Okay, we are live now. Um, we're gently getting started, so people will be arriving. If you are uh, arriving if people arrive a little bit late, it's not a big problem because I'm starting with a short recap of what we did last week, or sorry, on Monday, last lecture. So let's look at this. What we talked about. So we talked basically about something about techniques of integration and then started talking about differential equations. So a very quick recap. We had the basics of differential equations. There we talked about what is a differential equation. Basically, a differential equation is an equation where you have a function that is unknown, and then a function is constrained by an equation in which the derivatives of the function appear alongside with the function itself, maybe, and then possibly some expressions regarding the variable that with respect to which this function is evaluated. So for instance, we might have y, which is a function of x, and then we might have something like y prime plus y equals x squared, or something like this. So this would be the differential equation, in a nutshell. There may be, so we talked about these linear equations, logistic equations, separable equations. Those are basically the three classes of equations that we talk about. And the logistic equation is a special case which has its place in this analysis because it's very often used, for instance, in population dynamics. It's very often appears in control theories, control systems where there's like some kind of a limiting factor somewhere. Then there was the first order linear equations in which we were able to even provide an actual formula for solving it. So let's take a look at that. So first order linear equations are of the form where it's usually given in this form. So there's some function of x, ax, that is a known function. This could be like x squared or x plus 1 or e to the x or something, which is a multiple of this y prime, y being the unknown function that we are trying to solve, plus some bx times y, and bx is again the function of x. These could be constants as well, and very often we look at functions that have constants. And then on the right-hand side, it's usually c of x, some function of x. And here are some examples. We looked at these sort of examples, and we were able to solve this in these examples. Take a look at a couple of these equations. We talked about the standard form, which is easier to solve. If we have the standard form, it means that we kind of have this the coefficient that is the coefficient of the y prime. Then we transform that into 1. So we divide by basically the coefficient of the first derivative of y, because there's only this in this linear equation. It's fairly simple. So this ax, if you will. But with this, we kind of destroy the possibility to talk about the points where ax is equal, where this is equal to 0. So for instance, when here we have 3x squared minus 4, then x squared, when x squared equals 4 over 3, so that when x equals the square root of plus or minus the square root of 2 over the square root of 3, then we have the problem that this is going to be 0. So those points, after we've done this and put this in here, so for those points that are not where this 3x squared minus 4 is not equal to 0, we can talk about this equation. Well, usually what happens is that this, for instance, is not divisible, so it doesn't have a 0 at the same point. So this is already visible here, so that this is undefined and this is undefined because the denominator goes to 0. But be careful to make sure that you include all of them, because sometimes some of the zeros of this a of x, if you transform it, some of the zeros get lost. Like for instance, if this is, let's say this is x squared minus 1, and maybe there's x plus 1 here, and maybe x minus 1 here, and then you may do some of the manipulation of this, and you may lose the information that the 0 was somehow problematic. And then you come up with a function, and that function, you know, may work perfectly in those places, but and then if you try it here, then it really doesn't necessarily say anything about this function in that point. So be careful with that. So when we're dealing with this standard form of the differential equation, then we can more readily solve this. So when we write it like this, it's y prime plus pqy equals qx. So I'll go back here. So here are some of the examples. I urge you to look at them and so forth. So this so-called integrating factor it's actually not just in this case, but there are several situations where we use what is called an integrating factor. And the integrating factor is usually such that it allows us to solve part of the differential equation by using integrals. So it kind of binds stuff together to make it something that we can integrate. So in this case, for instance, when we multiply this by mu of x, which is suitably defined, then we can transform this, noting that we have this, if we have this y, which is unknown, and we denote that by f of x, then when we multiply it with mu of x, then we can notice that this becomes, because this is here in this equation, we can formulate a differential equation in its own right, which is a simpler one to solve, because noticing that if we take the derivative of this right hand side, it must be then we can and solve this for mu prime of x, then we get this mu prime of x must be equal to mu x times p of x. And the thing is, from here we can solve this mu of x. And once we do this, when we do this, this becomes now something that, because it satisfies now this equation, we found a function that satisfies this equation, and we punch it here into this. Then the left-hand side is simply the derivative of mu of x times y. I mean, it's using y, but it's actually y of x. And then the right-hand side is just mu times q of x. So this is easily solved by just integrating both sides. And that's why we call it the integrating factor, because if we multiply both sides with it, then we can actually just solve the whole thing by taking a certain integral. And we get here mu of x times mu is simply the integral of the right-hand side. So this mu of this y is then gained by dividing with this mu of x. And this mu of x is usually, in this linear case, this mu of x is pretty well behaved. I mean, it looks bad, but really it's not that bad. I mean, this p of x is usually very simple, so it's polynomial or something, or it's usually something that we can find the integral of relatively easy. If not, then this becomes hard. But let's assume now that it's some easy function whose integral is relatively easy to find. So when we get this e to the something, and this is relatively easy to find. It's notoriously easy if this coefficient p of x is a constant, because then it's just e to the a constant times x, if you find the integral of that. And we can fairly easily solve this, but there appears this e to the x q of x, e to the something x q of x appears here in the integral, and then we're just dividing with that mu of x. So This allows us with the strategy of solving really directly the first order linear differential equation. So basically, there is a tool by which we can solve the first order differential equation, linear one. Okay, here are examples. One example where we can go through this example now first. So this is not in the standard form. This is x times y prime plus 3y equals 4x squared minus 3x. Now, when we divide by x, we assume that x is greater than 0. So why we assume that it's greater than 0 and not just equal to 0? Well, one problem that may arise, I mean, we don't know, but one problem that may arise is that the result that we get is a function and it's smooth all around so that there's no problem crossing x equals 0. But it's not necessarily, you know, defined. The function, we cannot trust our solution necessarily at x equals 0. So if we don't assume that it's either greater than 0 or smaller than 0, then we may end up, you know, with solutions that don't match, because we may get from the negative side and the positive side, but they cannot meet. So this is just a bit academic. I don't have a good example now here because these linear equations happen to be such that usually it's fairly easy to do. But already here we see something. We assume x is greater than 0. We will be using this because we do we find that the p of x, when we formulate this into the normal form here, we find that the p of x here is 3 over x. So we calculate its integrand, and now the fact that we use the logarithm of x here, 3 times the logarithm of x, there we use the assumption, in fact, that x is greater than 0. Because if it could be smaller than 0, then we should have here the x logarithm of the absolute value of x. And if we take the absolute value of x in this case, then we have these, we end up with 2 solutions here. You know, the positive or the negative of x to the 3, depending on which side we are on. I mean, if x is negative, then this would be the negative of x to the 3. So we can just, assuming x is positive, we can dispense with this idea of are we taking the plus or the minus, okay? So that's where it appears. So now we have this integrating factor, happens to be a polynomial in this case. So very often the case, if we have something like this, there's an x factor here and a constant factor here, there's something over x, we get the integrating factor in this e to the something, it becomes a logarithm, and you know, this becomes a polynomial. That happens, so it's not always an exponential function. So we do this multiply both sides with this mu of x, and we get here left-hand side, right-hand side. So right-hand side is pretty obvious. Left-hand side becomes the derivative of this. I mean, this is one place where you can double check whether you calculated the integrating factor correctly. Because if you did calculate the integrating factor correctly, then after the multiplication, this left-hand side should become the derivative of y times the integrating factor. If it doesn't, then you've either calculated the integrating factor wrong, or maybe you've deduced this wrong, you know, backwards. You know, this. So make sure this is one place where you can double check. Then we take the integrands of both sides, then we get some polynomial plus c. And then, you know, remember this x to the 3 is still on the left-hand side, so we have to divide by it. So this constant here, that's now necessary. It's now necessary because the c x to the minus 3 is already now a function of x. So it's not just some constant that can be left out. I mean, this radically changes the function depending on what the constant c here is. This is not initial value problem, so we don't start with x equals 0 and know that what I mean, well, x equals 0 cannot be the starting point any case because we already ruled out that, but let's say x equal 1, if we had like y at x equal 1 is equal to, let's say 6, then what we would do is we would just punch in the numbers, replace x with that 1 or whatever x0 the initial value is, and then solve for this unknown c. So with an initial value problem, we need to solve this C, but this is not an initial value problem. So one thing to check is that if you have a first order differential equation, there will always be an unknown quantity there, a constant to be solved, and it can only be solved if you know one point through which this function is supposed to go. But once you know that point, then it's determined. All right. So this was an example of that. There are several examples here, and in the initial value problem, this is an example of an initial value problem. You do the same thing. I'm not going to go through all the details here. This was solved using an integrating factor and so forth. So you get here y is equal to 2x over 3 minus 5 over 9 times c times e to the minus 3x. So substitute x equals 0 and y equal 3, and you can solve this for the value of c, and you get the value of c like this. So there are other situations here. There were applications of first order linear differential equations. One was like if you have a ball with air, you throw a ball up and it comes down, you have air resistance, which is acts against gravity when it's going down, and actually acts in the same direction as the gravity when you go up. It's a little bit trickier than that. Here are some of the, here's another example where you can do this and so forth. And here are electrical circuits. I like these electrical circuits. I don't know if you know electrical engineering, have you studied it, but you know, it's already relatively simple, but it gives rise to really nice equations. So if we have a current that is going through a closed circle, so I'm just going to go through this. Let's say this is our closed electrical circuit. There's a voltage applied here, which is let's say it's a alternating current voltage, and then you know the voltage at any given point here is an unknown quantity. We know the voltage coming from here, but let's say the voltage across this either this inductor or this resistor is what we want to know. Then we formulate an equation. So let's go through this. This is a nice modeling task. So if we have a resistor here, the resistor works very simply that when there is current, then the voltage drops according to how much resistance there is. So you can think of voltage, I don't know how much electrical engineering you've studied, but you know, voltage, you can think of voltage as like, if you think of the current like a river flowing, right? Then the voltage is like how high, what is the height difference between the flowing starting point and the ending point. It's not a perfect analogy, but you can think of it like there's a height and the water tends to travel faster. And the resistance can be thought of as you know, depleting that speed, that energy, because the resistance, there's a certain flow of current. That's the I, that's the current. That's how much water there is flowing. So you know the resistance depletes that voltage. In order for the current to pass through this resistance, then it loses some of that voltage, some of that potential for pushing it forward. The thing about an inductor is that the inductor doesn't really resist the current as long as the current is not moving. It resists the change in the current. So an inductor works in a way that when the current flows through the inductor, what it does, it induces a magnetic field. So there's a magnetic field that arises like an electric magnet because of the inductance. I'm not going to explain this physics behind this, but you know the idea. And what happens is that as long as the current is kept constant, then the magnetic field doesn't change. And like the magnetic field tends to grab some of that energy that is in that electrical current, but once the magnetic field is established, it no longer resists the flow in any way. But when you try to change the current, so if you increase it, then it sucks a little bit of more energy into the magnetic field. So there's a voltage drop that is proportionate to the change in the current, not currency. So the inductor tends to resist changes in the current. Well, this capacitor works in a different way. So the voltage drop in a capacitor works in the following way. So if there's a flow of current through the capacitor, then it doesn't actually flow through it. Instead, the current is stored into the cumulative charge is stored into the capacitor. And as more and more charge is stored in the capacitor, then the higher and higher the voltage that is in the capacitor to oppose the flow of the current is. And once you reach the capacitance, then the voltage is the same but opposite to the voltage that is being applied, and no current goes through. So the voltage drop is basically proportionate to how much current has flown into the capacitor. So in other words, the derivative of this capacitance is really the current. So these are the three elements that form this electrical circuit. And now the loop rule says here basically that the voltage drop combined by this capacitor, by this inductor and this resistor must be equal to the output voltage. So all voltage is used along this circle. Now we can formulate this into we see the voltage drop here, the voltage drop of the inductor, the voltage drop of the resistor, and the voltage drop of the capacitor. So let's dispense with the capacitor now. So assuming there is no capacitor now, then because this Q is a bit awkward at this point, we can, let's say this is a so-called LR circuit, which means there's an inductance and a resistor. Then it comes down to this current through the inductor causes voltage drop of Li prime, this meaning the derivative of the current, and the resistor causes a voltage drop of Ri. And that is equal to the voltage, output voltage. If there is no capacitance, then this is an equation that describes the voltage through these elements. So it's now a first order linear differential equation. So here's an example of finding a current. So let's say that we have this is a 50 hertz voltage because it's, let's say T is given in seconds. No, it's not 50 hertz. Well, it's something, 20 times T. So if this is in radians, 42 pi, yeah, 600. This is about 100, what is this? 120 hertz, something like this voltage. In any case, let's say that we know the voltage is given by 50 volts times the sine of 20t. So as T changes, the voltage goes like this. It's alternating current. We have an inductor and a resistor. The resistor having 5 ohms and the inductor 0.4 henries. So we can formulate this so that it's the equation 0.4 times I prime plus 5I is 50 times the sine of 20t. Transform it into a normal form. standard form, we get a fairly straightforward differential equation. Then we can solve it. So here, find the integrating factor fairly easily. Solve it. There is a constant involved here. And let's say that we had the initial condition, was it given somewhere? Initial current is 0, all right? So initial current, why is V0 equal to 2? Didn't say that, no, initial. Well, I don't know what this means here. Because we get the solution here. This has sinus and sine and cosine, and then there is this exponential function here. We solved this for c equal to something like 400 something over 89, and then we notice that there is this voltage here, but this coefficient here, originally it seems to be if t equals 0, it's relatively large. But then it diminishes towards 0 as t goes to 0, to infinity, because this goes. So this is sinusoidal function. It has sine and cosine, but you know it's still a sum of these two. So it has some waveform is the same as the sine function, and its magnitude can be determined here. There's some angles here, but I'm not going to go here. That's given as this, so its magnitude is there, and it's cosine of 20 plus this phi, and this phi was probably somehow. So that's what's called the phase shift, and this is the cosine function. And then there was this, what is called the attenuation term. It's not a very big one, this attenuation term in this case. Someone has drawn this, so the attenuation term is relatively small. Yeah. All right, well, this example shows you how to do that. So let's go to then this second order linear differential equation, because I mean, why not? So the first order was, in the words of the Galactic Emperor, the first order was only the beginning. Ha ha. There's a terrible movie, by the way. So let's look at the second order linear differential equation, or second order differential equation. There are differential equations like there, but let's look at this firstly, this second order linear equations. So we were lucky enough to have first order linear equations that were fairly easy to solve. So we look at some of these situations. So let's first look at what we call a homogeneous equation. Now there's a little bit of a terminology clash in the realm of differential equations towards the word homogeneous. So I'm not going to talk about the other term, but you may later encounter another situation where they talk about homogeneous equations. So homogeneous means uniform in some sense. Of the same, homo means the same, or uniformness. So homogeneous means, you know, there is something uniform or something, you know, undisturbed or same levelness to it. In this case, it refers to the fact that this is homogeneous, meaning the only factors that are relevant are the factors of y prime, and y and y's derivatives. And there is no term on the right-hand side of this. So there are only terms that depend on y or its derivatives on the left-hand side, and on the right-hand side, there is nothing else except 0. This is what we call a homogeneous equation in this situation. So here, this is linear because y and its derivatives only have factors that depend on x, nothing that depends on y. So there's no y times y prime, there's no y squared, nothing like this. So that's why we say that it's linear. It's linear in y and its derivatives, meaning that y itself does not appear as a coefficient of something that depends on y. So this homogeneous equation and non-homogeneous equation, here are apparently the same versions. The thing about this is that if it's a homogeneous or non-homogeneous equation, then all these equations bear a huge similarity. And this also holds for first order linear equation as well. But here it becomes more prominent in that if we have a solution for the homogeneous version, then we can vary any variation in here, in this non-homogeneous version, can be absorbed, if you will, by the solution to the homogeneous linear equation. What I mean by this is, if you have a general solution to this, no matter what it is, let's say some f of x that satisfies this, if you put f in place of y and it satisfies this homogeneous equation, and then you have some g of x, which satisfies this non-homogeneous version, then f of x plus g of x always satisfies this. And that is simple because if you put f of x here on the left-hand side, then on the right-hand side, it becomes only 0. And you put g of x here, then out comes x squared. And because this is linear in y, then really, I mean, the sum, it's linear in the sense that if you punch in f plus x on the left-hand side, sorry, f plus g on the left-hand side, then out comes whatever f plus whatever does plus whatever g does to in the equation. That's why we say that it's linear, really. So, like I say here, the definition of a general second-order linear differential equation is of this form. We have something multiplying y's second derivative plus something multiplying y's derivative plus something multiplying y, and then something on the right-hand side. And if this right-hand side is 0, we say that it's homogeneous. And if it's not 0, then we say that it's a non-homogeneous equation. So here, let's look at some of the classifications. Here are examples. We can look at these situations, but let's say, first look at this A. This equation is not linear because it has the term y squared. That's not allowed. Only y prime, and y prime prime can be there, and their multipliers can only depend on x, never y. The second one is a linear, and it is homogeneous because there is a 0 on the right-hand side and nothing depends on x directly. C, this equation is nonlinear. It has the unknown x. That can be confusing. X can be placed, I mean, it's a notational convention. Of course, any symbol can be used in any place. But in this situation, very often, the case in in differential equations, x can either mean the unknown function, in which case usually the variable is t, because they usually use t because that's, you know, t evolves over time. If the unknown is y, then it might be x or t, but usually this is given. But because there are these primes and so forth on C, then x is the unknown function, but it's not linear because there is x times x prime in that equation. D is linear. It's non-homogeneous because the right-hand side has this 4x to the 5. E, that is non-linear because there is the sign of y prime. F, that is linear, and we can rewrite it in a standard form. So this 3t squared can be put on the right-hand side, so it's non-homogeneous. G, there appears to be no problem with this. It may look like it's a problematic with linearity, but it's actually not problematic with linearity. We can move all the y prime coefficients to the left-hand side and all the others to the right-hand side. Then we get this into the form that the sine of x squared y prime minus cosine of x plus 1 y prime plus x squared y equals -3. So it's a non-homogeneous linear equation. And in the last one, there is a cosine of y, and so that's not linear. All right, so this classification should be fairly simple. So let's take a look at here. So let's have a little bit of a break. I'm not going to have a lot of breaks today for you guys because we have lots of ground to cover, but let's do this first. Classify each of these following equations in 7.1 as linear or nonlinear. I'm going to give you 5 minutes for the group. So have a small group chat, minute or two, do the classification. We have this many, so I'm going to put you into rooms of 4 people. And classify these in 7.1, linear or nonlinear, determine whether it's homogeneous or non-homogeneous. And I'll give you 5 minutes, but use a few minutes of that to have a little chat about your weekend plans, about, you know, how things are going, and have a round where everyone gets to say something nice about this coming weekend. And after you've done that, then, you know, then discuss this situation. Is it nonlinear, linear? Is it homogeneous, non-homogeneous? All right. We reconvene at 45, 2:45. I'm back online now. So we can see that the first one here, we have y, second derivative of y to the power of 2. So it's definitely not linear. The B1 there, we have something that depends on sine of t, y prime plus cosine of t minus 3t y prime equals 0. Well, if we move this cosine of t on the right-hand side, we notice that this is in fact both linear and non-homogeneous. So let's look at this situation. You know, before we can solve the equation, we must be able to actually verify a solution to the equation. And it is done exactly the same way as before. So there is no magic involved. We just have to find the derivative of the derivative. So for instance, if someone proposes that y equals x to the 3 is a solution to this equation, then we can just try it out. So let y equal x to the 3. We calculate the derivative, which is 3 times x to the 2, and then the second derivative, which turns out to be 6x, and substitute this into the equation. It turns out to be 0, so that is in fact a solution. I'm going to leave this for now. We're not going to go there in too great detail. Here's a very fun fact or fun thing about this. If we have homogeneous equations and we have solutions to it, then one thing about it is that we can multiply this homogeneous equation solution with any constant, or we can add different solutions together to get also a solution. So if we have 2 different solutions to this, well, they could be the same, of course, as well. But if we get 2 solutions, y1 and y2, to a linear homogeneous differential equation, then any linear combination, meaning we multiply both by arbitrary constant and add these 2 together, will also be a solution. This is fairly easy to see and verify, given that you know, if we have this solution on the left-hand side, just punching it into this solution, if it results in 0, then multiplying with a constant results in a 0, because then, you know, the constant just comes out at every situation where there's the derivative. Also, when you add them, then it just taking the derivative, and the second derivative, these y1 prime and y2 prime just appear. So here, one situation is that we have e to the minus x and e to the 5x are solutions to this differential equation. We can show that 4 times e to the minus x plus e to the 5x is also a solution. And well, fairly easily observed, but you can also observe that these two are separately, and you know immediately that their linear combination is also a solution. So at this time, this holds for any linear differential equation, be it second, third, fourth, or nth order. If it's linear, then this fact, this theorem 7.1 holds for all those. We don't have to prove those all that much. So here comes the situation which may be puzzling to some of you. I'm not sure how many of you have taken some vector calculus or linear algebra course, like with matrix algebra or vector calculus, or, you know, vector spaces courses. That would be helpful here, though it's not, of course, required. But there is a thing called linear dependence or linear independence. And with vectors, that's usually such that two vectors are linearly independent if you can't form a linear combination of them in such a way that the result is 0. So for instance, if you take in a plane in R2, if you take two vectors in a plane and they point in different directions, neither of them is 0, then they are linearly independent unless they point in exactly the opposite directions, because if they point in exactly the opposite directions, you just multiply other by 5. You know, you can multiply the other to make it the same length and add them together, you get a 0. But if they point in different directions, you can't combine them to make 0. I'm not going to go in depth into this idea, but the same definition can be formulated for linearly independent functions. So if someone gives you n functions, this could be any functions, and we say that these are linearly dependent, if you can find constants in such a way that you add these constants together, you multiply each by some constant, add them together, and the result is 0 over all x in whatever the region we are talking about. So it's not just that it's 0 at one point, but it's always 0, and all the terms cancel out. Then we say it's linearly dependent. And if it's not, so that this combination here, no matter what non-zero, of course, if we pick these c's all to be 0, then obviously it's 0, but let's say that they're not all 0, some of them are not, then this function is not 0, at least somewhere. So it's not always 0. Then we say that these functions are linearly independent. And the thing about linear differential equations is that the order of the linear differential equation, it has, if it's nth order, it always has n linearly independent solutions. So the first order linear differential equation has one linearly independent solution. So it may have if it's homogeneous, it may have a constant coefficient that you can multiply it with, but there's only one, and they all differ by one constant. But if you take a second order differential equation, then it has two linearly independent solutions, and you can, both of them can vary with any constants, and it's still a solution. You might say that the dimension of, I mean, there is credit to the idea that the dimension of the problem is, it's two-dimensional problem if you have second order linear differential equation. If you have third order, then there's 3 and so forth. two functions are said to be linearly dependent if one of them is identically zero or if one is a constant multiple of the other. This is the simplest case, but of course there may be several ones that are linearly dependent. Not going to go there in too great detail, but if we look at the general solution of the homogeneous equation of the second order, there will always be two linearly independent solutions. And if we find, conversely, if we find two linearly independent solutions, then all solutions can be found by varying these two solutions and adding them together. So in other words, what's the takeaway here is if you solve the linear equation, you will get two constants there. That's what's going to happen. The second order differential equation, if you have a solution, it will have two constants that you need to vary. So for instance, if we have e to the 3t, e to the 3 minus, to the minus 3t solutions to this equation, they are in fact solutions, y prime prime to minus 9y equals 0. The general solution will be something times e to the 3t plus something times e to the minus 3t. And if these are general, and now I'm not going to go into the way we can solve them. Well, I can't go there because there is no freaking way we could solve a general second order linear differential equation unless the coefficients are constant. If they are not constant, then there are tricks and tips and tricks that we could do, but in general, even if we can transform it into the standard form where we have this y prime prime and then all the others are just, only the others are functions of x. Even if we could do that, then there is really no general solution. There are situations where we can find a solution, but generally speaking, the second order linear differential equation is already out of bounds so that we don't have a generic solution for those. This whole thing changes if we have constant coefficients in this equation. So if they're not functions of x, these coefficients, but constants, then it all changes, and then we are in the clear. Then we can solve it. In fact, it doesn't matter how high an order or differential equation is. If it has constant coefficients, we can actually always solve it. That's the good thing about linear differential equations. I'm not going to go there in this course. There was a course, it's a whole course on differential equations, and we actually talk about this linear differential equations when there are any number of these unknown or these coefficients. In here we have a, b, and c as constants, but we have this. And if it's of this form, or if there's a function here, there can be pretty much any function here, we can still solve it. But these need to be constants, these multiples of this y prime and y and y prime prime. So here comes the part which I don't that much like. And I'm sorry that I have to say this. So this seems like a gimmick. And in this situation it is. It would be much nicer for me to show this if I could put this into a matrix form. If I could put this into a matrix form where we have a matrix, usually this is given in matrix form in such a way that we have that A x prime equals zero or equals b, something like this. Usually we do it like this, where x is a vector format of this, and we have this. But I'm not going to go there because we don't have the scope here. So I'm just going to tell you that the characteristic equation turns out to be, in this case, it would turn out to be the characteristic equation of us finding a certain eigenvalues of this matrix. And I'm not going to go there, but I'm just telling you that if you study this further, you will find a much nicer and reasonable theory of why this is so. But at this stage, I have to resort to a little bit of a gimmick because we don't have the time to build the whole theory. There's a big theory from which we can then determine these things. So let's look at this. So we are not going to go here because this is a thing, but it's all based on the idea that, look, think about the derivative. Let's call this capital D. Let's say this is an operation, capital D now. So if we do a df and we find solutions to the idea that the d derivative of f is equal to, let's say, some constant, let's say a times f, then what kind of functions have this property? Well, that would be f of x is equal to e to the a of x, right? So if we find the derivative of this, then the derivative of f of x is a times f of x. So the derivative in itself is an operation that is a linear operation, right? But it's also this nice idea here works in this way. So we do this. Let's not use a, let's use L. It was using lambda here, so let's use L. So we want to find d of f or d of y is equal to L times y, okay? So we are looking for values like this. And then when you do the dd, this is the second derivative, so it's L equals L squared y, right? So now if we have a y prime prime plus b y prime plus c y, and that needs to be equal to 0. So we look for situations where this L, if we take this second derivative and we assume that the function, the solution has this property that if you find the derivative of it, then it's constant times something. We don't know if it is, but let's assume that it is. So we have this y prime prime is then L squared y, right? And y prime is equal to Ly. Now, if we do this and punch it into this equation, we get that a L squared plus b L plus c times y is 0. Now we know that this function y, we could always punch in here y equals 0. We would be happy with that, and that would be a solution, but we look for a function where this y is not 0. So let's assume y is not 0. Well, this is a product, and the product is 0 only if one of them is 0. So we look for the solutions of y L squared plus b BL plus C equals 0. So we look for solutions of this, and we solve for this L. So here's that what is called the character. That's why it's a characteristic equation. And look, if you knew matrix algebra, you'd know that we would, when we would be, sorry, that shouldn't be B, so that should be a to the x prime equal 0. But forget about that. If we were to talk about the situation where ax equal lambda x, sorry, ax, sorry, like this, where L is now not a matrix but a constant, then this is known as the eigenvalue equation. I'm not going to go there, but I mean, it's a much nicer place to look for solutions of this. So, but I hope that I were able to convince you that this makes sense to look for the characteristic equation. If we are thinking that the solutions might be exponential functions in form, then we look for them by finding this characteristic equation. And when we find the roots of this characteristic equation, it might have one or two roots. So if it has two distinct real roots, e to the, lambda 1 and lambda 2, then we have two linearly independent solutions. We can verify this fairly easily. I just wrote it, what I wrote in the chat window actually is a proof of that, that if we have this e to the Lx, then if L is a 0 of this characteristic polynomial, then if we have e to the Lx, then that is a solution of this differential equation of the original homogeneous differential equation. So if we have these roots, then we can find, and we have two linearly independent solutions, and we're done. So this is fairly easy. It comes, so solving second order linear differential equation with constant coefficients comes down to solving a quadratic polynomial, the roots of a quadratic polynomial, and that's all it is. So there's nothing to it. We're done. Well, of course, we're not done by far, because the thing is, there is a possibility that we have a situation such as, let's say the equation is y prime prime plus 2y prime plus y equals 0. Then we solve the characteristic equation, we get that L is -1. But we now don't have a we only have one root, and we don't have two linearly independent solutions. But it turns out that we can do a trick here. This trick is really hard to justify algebraically without resorting to matrix algebra, but I will try my best. So if we have just one root, then what else might satisfy this problem? So we had this solution. We were looking for y of x equals e to the, I was using L, but let me use k here. I'm using kx, right? So let's say kx, and k satisfies the characteristic equation because L looks so much like 1. So if we have y of x is equal to e to the kx, and it satisfies this equation, and let's say that, for instance, we have this a y prime prime plus b y prime plus c equals 0, and we have that this a k squared plus bk plus c is 0. So we have this. This is satisfied, but you know, this is something like there is only one root. There is only one root. There is no other solution to this. So in essence, let's say that the characteristic equation is, let's take an example. It's easiest. Let a equal 1, b equal 2, c equal 1. So I'm taking this as an example so that k is equal to -1. So we have e to the minus x satisfies this. But this is only one solution. We promised that there would be two. So can we find a function that mimics kind of this situation? And the thing is that yes, we can. If we take y of x, let's say u of x is equal to x times e to the power of minus x. Then we have u prime is equal to, well, this is e to the minus x plus e to the minus x. So that's in fact u plus y. And similarly, u prime prime will be equal to, well, it will be equal to, sorry, that, no, not that, it's not that, there's a minus missing. I made a blunder here. I was supposed to have a root. So u prime is not that, it's minus this, it's minus, so plus, right, it's this. So it's in fact minus u plus y. And then if we find the derivative of this, if you find the second derivative of this, u prime prime, well, that will be u minus y plus y. So let's find the derivative of that. We have this first one, we have x times e to the minus x minus e to the minus x minus I did a really bad number here on myself because I should have really just I should have just used k equals 1. I should have done it so that k is equal to 1 because I get really bad with these minuses. Well, you can try then it should satisfy this this equation readily. No, that cannot be correct. Is that? Let me see. You were x. No, it should be there should be, sorry. There should be a plus here. So that will be in fact u of x. So it kind of grabs that y in between when we take the derivative, but then it just goes away when we do it again. And if we punch this into this this function, then we're actually going to be just introducing u's and y's in there. So all the solutions will be formed by, in this case, the e to the kx or lambda x plus then x times e to the lambda x. And this is nice. It happens nicely and very easily. Well, then we ran into this trouble then. What if this doesn't have a real not-valued solution? Then we get complex roots, don't we? So we get complex roots. Here is the infamous I equals the square root of -1. I would much rather say that I squared equals -1, but I wouldn't use the square root function here, but don't worry about that. Well, the same thing applies. We can just use the complex roots here. But the thing about the complex roots is that we have what is called the Euler's formula. And Euler's formula works nicely because then we have e to the I being the imaginary unit ix, then that's equal to the cosine of x plus I times the sine of x, right? So that's called the Euler's formula. And, you know, with this, we can transform this into a general solution where we have the constant part, sorry, the real part of it, and then the imaginary part of it. And we can express the imaginary part in terms of cosine and cosine and sine. And the thing is, well, this is all a little bit wibbly wobbly because I don't like this way, the way it's done here, but never mind that. then it becomes just some linear combination of the sine and the cosine function inside here. So if we have, for instance, if the roots are 1 plus or minus 2i, then we have this 1 here. It becomes out as exponent, and then these come out as imaginary. If this real value here is 0, so if it just has imaginary roots, which may happen, like if we have like y prime prime plus y equals 0, right? Then we get the characteristic equation becomes k squared plus 1 equals 0. So it's k equals plus or minus I. So if we had this, then the solution will simply be C1 times the cosine of x plus C2 times the sine of x. And you can verify this actually is not, this happens very often, and we'll see some examples of when this happens. All right. Here are examples. Not going to go through these examples in great detail. Here are 2 examples, and let's you guys do this in a group setting. And this time I'm giving you 10 minutes to do that. It doesn't matter, do one of them properly. And if it's hard, focus on the first 7.6a, if you can do that. If you can do that easily, move on to B within that group. And I'll give you, how long should I give you? Maybe I give you 7 minutes. All right? Work that out, 7.6. I'll give you 7 minutes. All right. That was the first one. Okay. So this didn't have the roots of that characteristic polynomial was 1 plus minus 3i. I can believe that. I didn't do that myself. What about the second one? The second one looks not sure, but it looks it. All right, yeah, this is not a problem. The main point here is you formulate the equation. So in the first one, you find the characteristic equation. You solve the k squared plus minus 2k plus 10 equals 0. So you solve the second order polynomial and you got that. So the second one, you solve k squared plus 14 k plus 49 equals 0. I would care to venture that this is in fact going to be it's going to be k plus 7 squared equals 0. So we get k equal to minus 7. Isn't that actually pretty obvious? So the solution is C1 times e to the minus 7x plus C2 times x times e to the minus 7x. It's probably the solution. I didn't double check, but it looks like that. So I jumped here. So now you see you get these two. There are the linear differential equation. In this case, the second order linear differential equation will always have 2 constant coefficients. And because it has 2 constant coefficients, then in order to solve the initial value problem, or what is called the boundary value problem, either one, you will then be able to solve it if you have 2 constraining coefficients. The initial value problem, meaning you have to know both the value of the function at t0, and also the value of the derivative at t equals 0. Alternatively, you might find the value of the function in 2 points, t0 and t1. Then it's called the boundary value problem. The boundary value problem often arises from a mechanical situation where you need the function to be, you need the function that goes through 2 different points, let's say here and there, and you know that the function is going to be this here and that there, and then the derivative is not really constrained. And the initial value problem is often resolved in a kind of physical setting where you know, let's say, the initial velocity and place of something, or you know the initial voltage and current. So when you turn on a circuit, for instance, you turn on the voltage, it's initially everything is 0 and it goes on, for example. Or that you have a physical system where there's a suspended, let's say, spring, and you pull it, and then when you let go, you know, then that's the time when the time starts, and that's an initial value problem. And then boundary value problem, like I said, is something like, let's say you have a design problem, you need to fit the function here, and you need to fit it here, and then it goes through these points. So there is a thing about knowing, you know, when you formulate something or model something with a linear or any kind of differential equations, then it's very important to know whether these functions actually have solutions. I mean, it's one thing if you have this problem that is fairly easy to solve, like this linear equation, and you know that it has solutions. But what if it doesn't? And there are strong theorems, ones that we don't have to go through in this course, but there are all these sorts of theorems that state, they're usually called existence and uniqueness theorems. And usually they state that in certain situations, boundary or initial value problems have solutions. And as a general rule, the initial value problem is usually well behaved, in the sense that the initial value problem, so you know, let's say you have second order differential equation, you know the initial value of the function, you know the initial value of the differential equation, then there are rather general theorems that promise the existence of a solution to your equation. For boundary value problems, this is not necessarily so. So if we know 2 boundary conditions, it may not be possible to make your function go through these points. So as an example, we may have a boundary value problem where we have e to the power of something negative, let's say, and the initial value makes the function such that it's fairly very hard to make that function go any higher, and then the other boundary value problem is somewhere in a higher. So you have let's say x equals 0, it's this, x equal 5, it should be this, and then it's really hard to fit your function, or you may not be able to find these coefficients. But for initial value problems, so let's say that you know y at 0 or y at some point, and you know the y prime at that same point. So this is called the initial value problem. If you know that, then they usually have this solution, and there exist the unique solutions. But for boundary value problems, it may be the situation that we encounter unique solutions, or we encounter many solutions, or we encounter no solutions at all. So there are these 3 possibilities. There is some solution, and the solution is unique. There is some solution, but there are many solutions, and there are no solutions. So if you think of an engineering problem, then it's really very nice to have a solution there may be something fishy going on if you have several solutions, 2 or even infinite number of solutions, then you may have a problem that there in terms of designing a system that has many solutions, because you may not know which solution to use, or if you physically build a system and you try to figure out how it's going to behave and you get many solutions, that it may be that among those solutions there is some solution that is pathological, like some value goes to infinity or something, which means basically if you have, let's say, an electric circuit, you plug it in and then it just, smoke comes out eventually and it just, everything goes awry. But with boundary value problems, this may be a problem, but with initial value problems, this usually is not a problem if it's one of these more common equations, and pretty wide range of differential equations have this property that the initial value problem has a unique solution. Here are some examples I urge you to go through. We are shortly going to run out of time. There are situations where you can graph the solution. So here's an example of sine and cosine appearing. There's a complex solution. The thing is, in engineering tasks, you are very often interested in whether or not a function value goes through some threshold, whether it may increase over some limit, or whether it oscillates, it just goes back and forth, or whether it's stable in the sense that it approaches zero and so forth. Usually we talk about stable in the sense that the exponential terms here, the e to the something, they always have negative coefficients. It means that even if there's the sine function, the cosine function, then those kind of functions, those kind of solutions tend towards zero, which in this case you have the sine 2x function here, but because this e to the minus 3x is so dominant here that any oscillation is almost invisible in this when it goes below zero somewhere in here, but not by much. So here's an example of an initial value problem representing a spring mass system. So this is the last thing we discussed today. So this is a modeling issue, and we will then be discussing this a little bit more in next week as well. So if we have a spring mass system, well, the situation, it's not described here very well. It seems, let's see. Let's see if it's, well, it's given here. So this is so simple harmonic motion. So we have a natural spring position. So the more you perturb this from its rest position, then the more force this spring will apply to that point. And if you apply a mass into it, which is then drawn down by the gravity, then the force that is exerted by the gravity on this mass pulls the string down until the force of the string pulling up is equal to the gravitational force pulling the mass down. Now, in this place, it's in what we call an equilibrium. It means that in this situation, this mass won't move because it's there. It just doesn't move. If you pull it down a little bit more, a little bit off, let's say x from this equilibrium point, then the force in this spring will increase. So it will pull it up. So, and if you let it go, it will bring it back up. And that the force will diminish while it's going up. It may go above this, but then it's going to start pushing down, and it goes back down again, up again, down again, up again. If there is something attenuating this oscillation, meaning that maybe the spring, there's a certain internal friction in the spring, maybe there's a air resistance, maybe there are both, something is sucking energy out of the system. So the spring should stabilize eventually to this equilibrium point. Now, if we take all these forces and all these factors into account, we can formulate an equation that describes the motion of this mass. And it turns out to be a differential equation, because the force imposes well, when force is imposed in the equilibrium point such that they're not equal, then that causes acceleration of the mass. So if we're not in the equilibrium point, there is a net force applied to the mass, and that means that it starts accelerating. And acceleration, as we know, is in fact the second derivative of position, right? Velocity being the first derivative of the position. So how is the position changing? And then and if we have these forces acting on it, so there's the force applied by the spring and the force applied by the gravity, because the gravity, the force applied by the gravity can be thought of as a constant. We can just offset it from the equilibrium. So we can think of that in this equilibrium point, the force is 0. When we are above it, the force grows downwards. If we are below it, the force grows upwards. And it's the magnitude, it's the order of magnitude of how far you are from that equilibrium point. It doesn't matter which side you are, that force is equal. And then, and opposite in direction. If you are above, then it's down. If you're down, then it's up. And then there is another force, which is, let's say it's the air friction or the air resistance, and that's proportionate to the speed. So there is a force applied, but it's proportionate to the speed at which this is moving. So we can formulate this so that this displacement of this mass from its equilibrium point is in fact, it imposes a force that is proportionate to some k times the displacement. That's that's how springs are usually modeled. So the further you pull, the bigger the force. So you get that the m times x prime ma, this F. So you F equals ma. The right-hand side is the force, and left-hand side is the acceleration. So if you, in the equilibrium point, the equilibrium point S, and X is the perturbation from X. At the equilibrium point, the two forces Ks and mg cancel out. So the only thing is left that Kx plus mx prime equals 0. And this turns out to be that turns out that this can be thought of as having a characteristic equation, and we have here that we have that m. This has k, so I'm going to use, let's use w. It's actually omega, but mw it's not it's pretty bad. Let's use u. Mu squared plus ku equals 0. So we can solve this, and we get this u as equal to the square root of k over m. Well, it's given here as angular frequency. So in this case, we can think of this as being equal to, we can rewrite this equation, because this u is the square root of k over m, and then we can rewrite this equation like this, and we come up with the general solution to this equation, because in this case, the zeros of the characteristic equation of this one is simply the I times omega. So sorry, I wrote this wrong. So W equals square root of K over M, right? I wrote this wrong. So let that be W, not U. Then if we rewrite this, we come to a conclusion that U squared plus W squared U, sorry, W squared equals, so I wrote this characteristic equation. It's not U squared times Clay, it should be sorry. Let's forget about that. I wrote this wrong. So my original characteristic equation is M squared U plus, this is the characteristic equation, right? The U doesn't appear there because it's not the, it's X, it's not the first derivative of X. So if we rewrite this as U squared plus W squared is 0, then its roots will be U is plus or minus I times W. And then when we punch these into this formula, we get the general solution where there's the cosine of WT, or, you know, this is omega t, plus something times the sine of omega t. And this is when there's no attenuating force at play. But if there's a, let's see if this model has attenuating factors into it. Let's see. I didn't double check. Damped vibrations, yeah, so dampener. So if you have some dampening coefficients there, so usually this can be expressed as B times X prime. So this is a force that comes from, let's say, because of speed. So this is the net force by gravitation. The mx prime prime is the net force by gravitation and the spring. This is, sorry, this is the net force, the force that causes acceleration. Here is the force that causes attenuation of it. And here is the force, net force caused by the spring. And these must all cancel out to be 0. So formulating the characteristic equation like this B is some coefficient that's called the dampening coefficient. And if this dampening coefficient is positive, and these are suitably chosen, these are also assumed to be positive, then what results in here is a solution. And usually what happens is that this, the real part of this is negative. I mean, if this is a positive factor here, then the real part will be negative, and it will have this oscillating behavior, just like we would imagine, and it dampens very well. It may dampen quick enough so that it just goes to 0 immediately, or it may have oscillating behavior depending on how big that dampening factor is. Here are some situations that you can do. Then you can look at these. Here was the under damping, meaning that it just goes towards 0, but it has time to oscillate. Here you can look at this. This is a very good engineering perspective for that. We don't have time, sadly, to discuss this, but this is actually a very nice situation for that. And then there is the under damped, over damped, and critically damped situation. Look at those. There's actually very nice nice situation. All right, we seem to be running out of time a little bit here. So I won't go any further here. I'll just go back to this second order differential equation. Here are some examples. I urge you to look at the examples of the boundary value problems and such, and I'll put some of these exercises for next week. The non-homogeneous linear equation, we'll talk about that a little bit on Tuesday. And then I will try to move on towards the series and those sort of things. I will try in the last week also to talk a little bit about the stuff that we omitted because we were running out of time, such as the those integrals where x goes to infinity, or integrals where the function goes to infinity. We didn't talk about those. That requires a little bit of a discussion on limits and so forth. So we'll do that as much as we have time. But this is about as hard as it gets. So I'm not going to be expecting you guys to be able to solve anything more complicated than linear constant coefficient second order differential equations. We may look at this non-homogeneous situation a little bit, so maybe that is something in there, and we'll look at situations in which they might arise. All right. Okay, that concludes this lecture. So I'm going to stop here. I'm going to put this recording stop.